Advanced Nuclear Fuel Economics and Supply Chain, a research report prepared by the Innovation Attorney, March 2026. Executive Summary. The advanced nuclear energy sector is undergoing a pivotal transition. Vendors of small modular reactors, SMRs, and advanced reactor designs are racing to attract private capital, government backing, and utility commitments on the promise of safer, cheaper, and more flexible nuclear power. At the center of nearly every advanced reactor value proposition is a fuel choice that almost uniformly departs from the conventional uranium dioxide, UO2, pellet and zirconium rod design that has powered light water reactors, LWRs, for 7 decades. Those departures include TRISO, tristructural isotropic, fuel, metallic uranium zirconium alloy fuel, and ceramic metallic, CERMET, composite fuel. Each offers genuine technical advantages over conventional UO2. Each also costs substantially more to produce, depends on a supply chain that does not yet exist at commercial scale, and faces regulatory pathways that remain partially uncharted. The conventional nuclear fuel cycle is genuinely cheap. LWR fuel elements cost roughly $300 per kilogram to fabricate. Enriched uranium at 5% U-235 concentration costs approximately $3,000 per kilogram. The entire fuel cost, mining, conversion, enrichment, and fabrication, represents 15 to 20% of a nuclear plant's operating expenses. That baseline is the product of 7 decades of industrial refinement, automated production supplying approximately 400 reactors worldwide, and rejection rates below 1%. Against that baseline, TRISO fuel at approaching $30,000 per kilogram and metallic HALEU fuel whose feedstock alone exceeds $15,000 per kilogram represent a fundamental economic challenge that the advanced nuclear industry must address openly and rigorously. On the regulatory side, the field is seeing genuine forward movement. TRISO-X, a subsidiary of X-Energy, received a first-of-its-kind NRC license under 10 CFR Part 70 in February 2026, the first new nuclear fuel facility licensed in the United States in more than 50 years. Oklo Incorporated has completed an NRC pre-application readiness assessment for its Aurora fast reactor combined license application. The Department of Energy committed $2.7 billion over 10 years to expand domestic uranium enrichment capacity as of January 2026. The supply chain gaps remain large, however. The only currently operating Western HALEU enrichment facility, Centrus Energy's demonstration cascade at Piketon, Ohio, produces approximately 900 kilograms per year. A single Oklo 50-megawatt reactor would require roughly 11 years of that facility's entire output for its initial fuel load alone. Detailed findings. 1. The conventional nuclear fuel baseline. Understanding why advanced reactor fuel economics matter begins with a clear-eyed view of what those fuels must compete against. Conventional LWR fuel, comprised of UO2 pellets stacked inside zirconium alloy cladding tubes, represents one of the most refined industrial processes in energy production. Fabrication costs approximately $300 per kilogram of finished fuel assembly. Enriched uranium feedstock at 5% U-235 costs roughly $3,000 per kilogram. Total fuel costs, including mining, conversion, enrichment, and fabrication, account for 15 to 20% of LWR operating expenses, a figure that has remained remarkably stable through decades of industry optimization. The manufacturing process for conventional UO2 fuel is direct. Press the powder into pellets, sinter them in a kiln, load them into rods, backfill with helium, and weld the end shut. Automated production lines supply approximately 400 operating reactors worldwide with rejection rates below 1%. A single leaking fuel pin constitutes a reportable anomaly rather than routine operational noise. That level of precision, achieved at scale, represents the economic and operational benchmark against which every advanced fuel type is implicitly measured. UO2 has genuine limitations that motivate research into alternatives. As a ceramic, it transfers heat poorly. The temperature gradient from the outer surface to the center line of a UO2 pellet in a pressurized water reactor, PWR, can reach 1,000 degrees Celsius across a diameter of roughly 1 centimeter. The center line can reach 1,200 degrees Celsius, while the external coolant sits at 300 degrees. That margin seems generous given UO2's melting point near 2,800 degrees, but it shrinks rapidly in higher temperature reactor designs. In a high-temperature gas-cooled reactor, coolant temperatures already approach 800 degrees, and gas transfers heat less efficiently than pressurized water. The centerline can climb toward 1,800 degrees. UO2 also fractures under thermal cycling, creating fission gas release paths that constrain how aggressively reactor power can be ramped. A growing concern as grid operators seek nuclear power that can follow demand rather than run only at baseload. 2. TRISO fuel. Technical promise and manufacturing economics. TRISO fuel is, at its core, still uranium dioxide. A TRISO particle consists of a UO2 kernel roughly the size of a poppy seed, surrounded by a porous carbon buffer layer, an inner pyrolytic carbon layer, a silicon carbide, SiC, layer, and an outer pyrolytic carbon layer. Billions of these particles are embedded in a graphite matrix that also serves as the moderator. The geometry changes the thermal physics fundamentally. A poppy seed-sized sphere of UO2 has a centerline to surface distance measured in fractions of a millimeter rather than half a centimeter, and the temperature gradient across it is correspondingly small. The SiC layer provides structural containment with a melting point so high that even if the UO2 kernel were to melt under accident conditions, the shell would remain intact. TRISO fuel has an operational record from the German AVR and THDR, 300 reactors, and the American Peach Bottom and Fort St. Vrain plants. Fuel behavior in those programs was generally good. Significant difficulties arose in supporting systems rather than in the fuel itself. The only currently operating commercial TRISO reactors in the world are the 2 units of the HDRPM, high-temperature reactor pebble bed module, at Shidaowan in China, which achieved a capacity factor of approximately 20% in their second year of operation after 9 years of construction and a multi-year commissioning period. The manufacturing economics of TRISO fuel present a serious challenge. Producing TRISO begins with dissolving UO2 in acid to form a uranium nitrate solution, precipitating it into droplets, and calcining those droplets into UO2 kernels, which are supposed to be perfect spheres and frequently are not. Imperfect kernels must be chemically deprocessed to recover the underlying high-assay low-enriched uranium, HALEU feedstock, a step with no simple analog in conventional pellet production where off-spec material can simply be reground and reprocessed. The coating layers are applied by suspending kernels in a gas flow and powder coating them layer by layer across billions of particles simultaneously. Each layer has its own rejection rate, and rejection rates compound multiplicatively across the full production sequence. The cost consequence is severe. HALEU feedstock at approximately 20% U-235 enrichment costs roughly $15,000 per kilogram, compared to $3,000 per kilogram for conventional 5% enriched uranium. TRISO fabrication on top of that currently runs between $5,000 and $15,000 per kilogram under small batch production conditions. Though these estimates carry substantial uncertainty, total fuel cost approaching $30,000 per kilogram is a reasonable current estimate against the approximately $3,300 per kilogram for conventional UO2 assemblies. Whether automation and scale can substantially reduce that cost gap is the central unresolved commercial question for TRISO-fueled reactor designs. Current producers include BWXT, X-Energy's TRISO facility, and Standard Nuclear, formerly associated with Ultrasafe Nuclear. 3. TRISO regulatory milestone, the TRISO-X license. On February 13, 2026, the NRC issued TRISO-X, LLC, a subsidiary of X-Energy, a special nuclear material license under 10 CFR Part 70, the first new nuclear fuel fabrication facility licensed in the United States in more than 50 years. The license authorizes TRISO-X to receive, possess, process, and ship HALEU material throughout the complete fuel manufacturing cycle at its TX-1 and TX-2 facilities in Oak Ridge, Tennessee. TX-1, currently under construction at the Oak Ridge Horizon Center, following groundbreaking in November 2025, is a 215,000 square foot facility designed to produce 700,000 TRISO-X fuel pebbles per year and employ approximately 500 full-time staff. The license classification is significant. Under 10 CFR 70.4, TX. One is designated as a Category 2 nuclear fuel facility, the first such facility in the United States, reflecting the higher strategic significance of HALEU material, enriched to 10% or more, but less than 20% U-235, compared to conventional low-enriched uranium. Category 2 status requires enhanced physical security, material accountancy, and cybersecurity measures substantially more demanding than those applicable to conventional LWR fuel fabrication. The Federal Register entry for the license appeared on March 16, 2026. This regulatory milestone establishes the foundational legal framework for commercial HALEU fuel fabrication in the United States, though it addresses only the fabrication step and does not resolve the upstream enrichment supply chain challenge. For metallic fuel and the EBR-2 legacy, metallic nuclear fuel, typically uranium alloyed with 10% zirconium, offers a fundamentally different set of physical properties from UO2. Metal conducts heat orders of magnitude better than ceramic. The centerline temperature problem that constrains UO2 operation effectively disappears. Heat moves out of a metallic fuel pin quickly enough that operation at higher power densities is possible without approaching melting limits. The metallic crystal structure also retains fission products more effectively than the ceramic grain structure of UO2, because displaced metal atoms tend to settle back into the crystal matrix rather than occupying interstitial positions that open fission gas release paths. The Experimental Breeder Reactor 2, EBR-2, at Argonne National Laboratory, which operated from 1964 to 1994, is the primary operational reference for metallic fast reactor fuel behavior. In a landmark April 1986 demonstration, operators cut the primary sodium pumps at full power, simulating a loss of flow accident. The reactor shut itself down through inherent negative reactivity feedback as the expanding fuel geometry reduced reactivity. Power dropped to near zero within approximately 5 minutes without any control rod insertion or operator action. This demonstration is legitimately remarkable and forms the technical foundation of the passive safety case for sodium-cooled fast reactors using metallic fuel. The passive safety case has a boundary that its proponents do not always emphasize. What EBR-2 demonstrated was safety during loss of flow, meaning a loss of coolant pump operation. A loss of coolant event, meaning actual sodium leaving the primary circuit, is a considerably more severe scenario. Metallic fuel's lower melting point, substantially lower than UO2, leaves less time between coolant loss and potential fuel damage than UO2's large thermal margin provides. The passive safety case for metallic fast reactors is real. It is narrower than its most enthusiastic advocates sometimes present. EBR-2 also operated the fuel cycle facility, a physically attached reprocessing plant that closed the fuel cycle on-site through electrochemical processing. Spent metallic fuel was dissolved in a molten salt bath of lithium chloride and potassium chloride at approximately 500 degrees Celsius. An electrical current selectively deposited uranium onto a steel cathode while fission products remained in the salt. Turnaround times from fuel removal to reloading ran between 30 and 50 days. The process required all operations to be conducted through thick leaded glass, using remote manipulators in inert argon atmosphere, conditions that represent some of the most demanding industrial operations ever sustained in a research environment. 5. Oklo and the HALEU supply chain gap. Oklo Incorporated is among the most prominent commercial ventures pursuing the metallic fast reactor concept. Its proposed Aurora reactor, initially designed at 1.5 megawatts and now discussed at larger scales up to 75 megawatts electric, would use HALEU metallic fuel and eventually close its fuel cycle through on-site reprocessing of what the company describes as legacy spent nuclear fuel from the existing light water fleet. Oklo's 2023 investor guidance described an initial core requiring approximately 10 metric tons of HALEU for a 50-megawatt reactor, intended to last approximately 10 years before a reload of roughly half that quantity. The gap between that fuel requirement and current Western HALEU production capacity is dramatic. Centrus Energy's demonstration cascade at Piketon, Ohio, currently the only Western HALEU enrichment operation, produces approximately 900 kilograms per year. A single Oklo reactor at the parameters described in investor guidance would require approximately 11 years of Centrus's entire current output for its initial fuel load alone. The Department of Energy committed $2.7 billion over 10 years to expand domestic uranium enrichment capacity in January 2026, and other enrichment entrants, including Urenco and Desano, have announced expansion plans. But no commercial-scale Western HALEU enrichment facility exists today. Urenco's planned HALEU facility at Capenhurst in the United Kingdom targets production by 2031. Desano announced plans for 350 metric tons per year of HALEU production, with initial commercial samples by the fourth quarter of 2026 and large-scale production beginning in the first quarter of 2027. A separate supply chain constraint is the absence of approved transport infrastructure. As of early 2026, there are no approved casks that would permit economical transport of HALEU in the quantities required to sustain a commercial fuel cycle. The DOE awarded $11 million to 5 companies in 2025 to develop and license new HALEU transport packages. NAC International received NRC approval for the Optimus L transport package for HALEU TRISO contents, representing early progress on this specific challenge. But the broader transport infrastructure gap is real and compounds the enrichment supply challenge. Oklo's investor-stated fuel cost figure of $7,000 per kilogram does not survive scrutiny given these realities. HALEU at market prices already costs roughly $15,000 per kilogram before entering a fabrication facility. Achieving $7,000 per kilogram as an all-in fuel cost would require either a negotiated DOE subsidy, uranium prices significantly below current market rates, or reprocessing economics that no Western commercial experience supports. French LWR reprocessing at La Hague has consistently failed to compete economically with fresh uranium at current market prices. The gap is wide enough that EDF has carried its stockpiles of recovered plutonium and reprocessed uranium at zero book value since 1995, a formal accounting acknowledgement that those materials cannot be sold at any price covering the cost of conversion to usable fuel. 6. Oklo NRC licensing progress. Despite the fuel supply chain challenges, Oklo has made meaningful regulatory progress. In 2025, the NRC completed a pre-application readiness assessment for Phase 1 of Oklo's combined license application, COLA, for its first commercial Aurora powerhouse at Idaho National Laboratory, finding no significant gaps that would hinder acceptance of the application. The NRC accepted Oklo's Principal Design Criteria, PDC, topical report for review under an accelerated timeline, with a draft evaluation expected in early 2026, less than half the traditional review period. The Department of Energy also approved a nuclear safety design agreement for Oklo's Aurora fuel fabrication facility in November 2025. Oklo has stated a target of first commercial operations at INL in late 2027 or early 2028, a timeline that the fuel supply chain analysis above should inform. 7. Cermet Fuel, Russian operational experience and Western implications. Ceramic metallic Cermet fuel embeds ceramic UO2 particles in a metal matrix rather than pressing them into solid pellets. The metal matrix conducts heat substantially better than a solid ceramic pellet, reducing the centerline temperature problem. The ceramic particles retain fission products better than the homogeneous metallic pin because particle boundaries impede fission gas migration. Neither property is fully optimized in Cermet form, but both are meaningfully improved over either pure form. Russia has operated Cermet fuel in its nuclear icebreaker fleet continuously since the 1950s, accumulating more than 400 reactor years of operational experience. The current RITM-200 reactor, developed by Africantov OKBM and installed on 4 icebreakers with more under construction, uses a core of 199 fuel assemblies containing UO2 particles dispersed in a aluminum-silicon alloy, matrix enriched to just under 20% U-235. The fuel rods are clad in a nickel-chromium corrosion-resistant alloy chosen for its performance over long refueling cycles. The RITM-200 core operates for 5 to 7 years between refuelings in reactors that must handle continuous, aggressive power transients as icebreakers throttle against Arctic pack ice. That duty cycle would be severely punishing for conventional UO2 fuel. The Cermet matrix handles it routinely. The RITM-200's operational significance is difficult to overstate. This is not a laboratory demonstration, but working propulsion equipment operated by crews who cannot easily return to port if a fuel problem develops. The relative absence of this experience from Western advanced nuclear discussions reflects several practical factors. Russian reactor data is difficult to independently verify. The RITM-200 fuel is manufactured by Russian industrial infrastructure with no Western equivalent. The enrichment level, just under 20%, sits at the boundary of what Western nonproliferation policy treats as acceptable for civilian use. None of these factors diminish the technical significance of what has been demonstrated. They explain why it remains a footnote in discussions dominated by American and European vendor narratives. Lightbridge Corporation is pursuing a different application of metallic fuel principles, one directed at the existing LWR fleet. Their cruciform-shaped metallic fuel rod, designed to replace conventional UO2 assemblies in operating PWRs without requiring HALEU, is now at the test rod stage at Idaho National Laboratory. The helical cruciform geometry increases heat transfer surface area and improves coolant mixing. The metallic matrix's better thermal conductivity and fission product retention could enable higher power density, higher burnup, and longer operating cycles at conventional enrichment levels. The commercial appeal of this approach lies in targeting an installed base of approximately 400 operating reactors, rather than a fleet that does not yet exist. 8. Capacity factor assumptions and economic reality. Advanced reactor companies routinely project capacity factors in the low to mid 90% range in their commercial projections. The current U.S. nuclear fleet does achieve approximately 93% capacity factors. That performance level represents the result of more than 5 decades of systematic improvement, hundreds of reactors generating comparable operating data, industry-wide information sharing through the Electric Power Research Institute, EPRI, and the Institute of Nuclear Power Operations, INPO, sustained regulatory attention to failure modes, and multiple fuel vendors competing on reliability as well as price. Early generations of LWRs did not achieve 90+% capacity factors immediately. An advanced reactor running on TRISO or metallic fuel will not arrive at 93% capacity in its first operating cycle. The HDRPM at Shadaewin, the world's only currently operating commercial TRISO reactor, achieved approximately 20% capacity factor in its second year of operation, following 9 years of construction and a multi-year commissioning period. Every new reactor design encounters failure modes that simulations and laboratory testing cannot fully predict because the interaction between fuel behavior, reactor conditions, and supporting systems only becomes fully legible under real operating conditions. The cost of learning those lessons falls on whoever finances the early units. The fuel cost question and the capacity factor question are not independent variables. A reactor running at 20% capacity factor with HALEU fuel that costs 10 times the conventional alternative is extracting a small fraction of potential revenue from a very expensive input material while paying that material's full cost. The advanced nuclear economic case does not become compelling simply because reactor construction costs fall. If fuel costs are simultaneously high and early capacity factors are simultaneously low, investors, utilities, and policymakers evaluating advanced nuclear propositions need to stress test both variables together rather than treating them as separate line items. C. Legal and regulatory implications. 1. NRC licensing framework for advanced nuclear fuels. The NRC regulates nuclear fuel materials under 10 CFR Part 70, which governs domestic licensing of special nuclear material. Conventional LWR fuel fabrication facilities are typically licensed as Category 3 facilities, handling low-enriched uranium below 10% U-235. Advanced nuclear fuels using HALEU, 10 to 20% U-235, require Category 2 facility licensing, which carries substantially higher physical security, material accountancy, and cybersecurity requirements. The TRISO-X license issued in February 2026 is the first Category 2 fuel facility license in U.S. history and the first new fuel fabrication license of any kind in more than 50 years. Advanced reactors themselves require either a combined license under 10 CFR Part 52, covering design certification, site permit, and operating license in a single proceeding, or, in some cases, licensing under the Atomic Energy Act provisions that the NRC is applying to novel designs under its Advanced Reactor Program. Oklo's Aurora is proceeding under 10 CFR Part 52 with a combined license application. The NRC's 2025 acceptance of Oklo's Principal Design Criteria Topical Report under an accelerated timeline reflects an institutional commitment to streamline review of advanced reactor applications, though the accelerated schedule still contemplates a multi-year process before a license would be issued. 2. HALEU. Legal and Policy Framework. HALEU occupies a distinctive legal position. At 10 to 20% U-235 enrichment, HALEU is not weapons-grade material, which requires 90% or more enrichment, but it requires significantly more safeguards than conventional low-enriched uranium. The Nuclear Non-Proliferation Act of 1978 and associated NRC regulations require specific protections for Category 2 quantities of special nuclear material. Export and import of HALEU are subject to Nuclear Regulatory Commission licensing under 10 CFR Part 110, and international transfers are governed by 123 agreements between the United States and recipient nations under the Atomic Energy Act. The current absence of approved commercial-scale HALEU transport casks is both a practical supply chain problem and a regulatory gap. Without licensed transport containers in adequate quantities and configurations, HALEU cannot move efficiently from enrichment facilities to fuel fabricators to reactor operators, regardless of production capacity. The HALEU Act of 2023, enacted as part of the National Defense Authorization Act for FY 2024, directed DOE to make available specific quantities of HALEU, 3 metric tons by September 30th, 2024, an additional 8 metric tons by December 31st, 2025, and an additional 10 metric tons by June 30th, 2026. These statutory mandates reflect congressional recognition that government action is necessary to break the chicken and egg dynamic. Private enrichment companies cannot commit capital without assured demand, and advanced reactor developers cannot demonstrate assured demand without committed supply. Whether those statutory targets will be met under current administration priorities and budget constraints is an open question as of March 2026. 3. Reprocessing. Regulatory and non-proliferation barriers. Metallic fast reactor designs from Oklo and others envision eventual on-site reprocessing of spent fuel through electrochemical processes derived from the EBR. 2. Fuel cycle facility experience. Commercial nuclear reprocessing in the United States was prohibited by executive order in 1977 due to proliferation concerns about separated plutonium. That prohibition was lifted in 1981. But no commercial reprocessing has occurred in the United States since the 1970s. Any commercial reprocessing operation would require an NRC license under 10 CFR Part 50 or Part 70, depending on the scope of the activity, an environmental impact statement, and likely congressional engagement given the policy sensitivity of the issue. The electrochemical process used at EBR-2's fuel cycle facility deliberately left plutonium and higher actinides mixed with rare earth fission products as a non-proliferation measure, because the resulting mixture is unsuitable for weapons use without additional separation steps that would be detectable. Whether this approach satisfies NRC and IAEA safeguards requirements for a commercial-scale facility operating outside of a national laboratory environment is a question that has not been definitively resolved in an NRC proceeding. The regulatory pathway for commercial pyroprocessing is materially unclear. 4. Compliance and liability considerations. Operators and investors in advanced nuclear facilities must account for several compliance and liability dimensions beyond reactor licensing. Nuclear liability under the Price-Anderson Nuclear Industries Indemnity Act 42 U.S.C. Section 2210 applies to licensees and provides a layered system of insurance and government indemnification. Advanced reactors are subject to Price-Anderson coverage requirements, and HALEU fuel fabrication facilities handling Category 2 material carry enhanced security and liability obligations. Investors should model the incremental cost of compliance with Category 2 physical security requirements, which exceed conventional LWR fuel facility costs, as part of any capital allocation analysis. D. Open questions. 1. Will automated TRISO manufacturing at commercial scale achieve the cost reductions necessary to close the gap with conventional UO2 economics? The transistor analogy is appealing. Semiconductor costs fell by orders of magnitude as demand drove automation and process refinement. But semiconductor demand created entirely new categories of human activity. TRISO-fueled reactors produce electricity and medium-grade process heat, products that the world already generates through dozens of competing technologies with mature supply chains. Whether sufficient concentrated demand will materialize to drive the necessary automation is the key, unresolved commercial question for TRISO. 2. Can Western nations build a commercially viable HALEU enrichment and transport infrastructure before the first wave of advanced reactors requires it? The DOE's $2.7 billion commitment, Urenco's HALEU expansion plans, and Nissan's stated production targets represent meaningful policy and private responses to the enrichment gap. But the timelines involved, 2027 to 2031, for significant new capacity, may not align with reactor deployment schedules, and no resolution of the transport cost deficit is yet complete at commercial scale. 3. What is the realistic regulatory pathway for commercial pyroprocessing in the United States? Oklo's fuel cycle narrative depends on eventually reprocessing spent fuel. No commercial pyroprocessing license has ever been issued in the United States. The NRC has not completed a rulemaking that would establish the applicable framework. This is a fundamental regulatory uncertainty affecting the long-term economics of any design that anticipates closing its fuel cycle. 4. How will advanced reactor capacity factors evolve through initial operating cycles, and what does that trajectory imply for fuel cost competitiveness? The HTRPM at Shidaiwan at 20% capacity factor in year 2 is not necessarily predictive of Western advanced reactor performance, but it is the only current operating data point. The sector lacks the fleet-wide data accumulation mechanisms, INPO EPRI, that produced the 90+% capacity factors of today's LWR fleet. The first commercial advanced reactors will incur learning costs that are real and not yet quantified. 5. How will the Russian Cermet fuel experience and the RITM 200 operational record factor into Western advanced reactor fuel qualification processes? The 400-plus reactor years of Cermet operational data represent the most extensive real-world database for a non-UO2 fuel form in existence. Western fuel developers cannot directly access or verify that data. Whether and how it will be recognized in NRC licensing proceedings for Cermet-type fuels is an open regulatory question with significant commercial implications. 6. Can Lightbridge's metallic cruciform fuel compete economically with the continuing improvement of UO2 through accident-tolerant fuel programs and LEU plus enrichment developments? A fuel that outperforms today's UO2 may still lose the economic competition if the conventional technology baseline continues to improve during the qualification period for the new fuel form. 7. What federal and state policy frameworks will govern advanced nuclear fuel production, transport, and waste management as the sector scales? The HALEU Act of 2023 addresses supply, but broader policy questions about federal liability coverage for novel fuel types, state siting authority for fuel fabrication facilities, and the regulatory treatment of spent advanced nuclear fuel remain incompletely resolved.